Our group was interested in the design and operation of an unmanned aerial vehicle. To begin the project, research was compiled on industrial, currently existing UAVs. The Cessna 172, a 4-seat single-engine aircraft, however, was used for most of the operational inspiration. The chosen cruising speed of 50 meters per second, the takeoff speed of 30 meters per second, as well as a cruising altitude of 10,000 feet were inspired by the Cessna 172 and similarly sized UAVs. The Cessna 172 has an approximate total weight of 757 kilograms, and our decided upon weight of the total aircraft was 1,000 kilograms.
Because the goal for our project was to create a UAV with the maximum flight time, it was determined that our airfoil would require a high lift-to-drag ratio. Airfoils with less thickness and a higher camber resulted in a higher lift-to-drag ratio. Therefore, airfoils following these guidelines were researched. After a comparison of several different airfoils, the NASA Prandtl-D was decided upon. For the Reynolds number of cruising conditions, approximately 2 million, it has a maximum lift-to-drag ratio of approximately 75, at an angle of attack of about 5 degrees.
The next step in the project consisted of determining other important factors of our wing design, such as the angle of attack, chord, and wingspan of the airfoils. As seen in this graph, the Prandtl-D airfoil achieves the greatest lift coefficient and therefore greatest lift at a 10-degree angle of attack. This angle of attack will be used during takeoff to ensure maximum lift. The necessary lift force was then determined by using the equilibrium equation at takeoff, which states that the total lift force will be equal to the total downward weight force of the body. Therefore, it was determined that the total lift force necessary must be greater than 9,810 newtons. Using the equation for the lift force, a necessary airfoil area was determined. Because area is calculated as the product of airfoil chord to wingspan, one of these values needed to be assumed in order to complete the calculation. A chord length of 1.5 meters was assumed, and using the calculated area of 14.83 meters squared, the wingspan for the UAV was determined to be approximately 10 meters. This value was rounded up to 12 meters to allow for more leeway within the lift. This value is in accordance with the modeled Cessna 172, which has a wingspan of approximately 11 meters. From here, the lift force during takeoff was calculated to be 11,907 newtons, which should be enough to get us off the ground. Now we need to calculate the drag. Looking back at the figure for the lift versus drag ratio compared to the angle of attack, we can see that we can achieve the highest ratio at about a 5-degree angle of attack, which would mean that this would be our most efficient angle of attack to fly at. Now, this graph shows the Prandtl-D's coefficient of drag values for any given angle of attack. As you can see, the coefficient of drag is pretty low at the angle of attack of 5 degrees. Therefore, the angle of attack for 5 was chosen for the UAV's cruising conditions, and the value for the coefficient of drag pulled from this graph. Using known values of the coefficient of drag, velocity, air density, and wing area during cruising, the drag force applied to wings could be calculated at about 46.519 newtons. To quantify the drag acting on the fuselage of the vehicle, the fuselage was assumed to be a streamlined body. Since the calculated Reynolds number was greater than the necessary value of 10 to the 5th, the drag coefficient for the streamlined body can be set at 0.04. This value was used to calculate total drag of the fuselage, and it came out to be about 5.601 newtons. Next, we want to calculate the power requirement and propulsion estimate for the aircraft. The power of an aircraft is defined as the product between velocity and drag force. For this calculation, a summation of the drag force acting on the wings and the fuselage was required. The power at cruising conditions was determined to be 3,104.95 watts. The selected propulsion method for our UAV was by propeller. After initial research, it was discovered that most propellers max out at an efficiency of about 0.8. With this knowledge and with the determined power, the engine power was calculated to be 3,881.1875 watts, or an equivalent of 5.205 horsepower. Commercial engines that could achieve this horsepower were researched. The team decided upon the Honda GX200, which has a maximum horsepower of 5.5 horsepower. The specs for this engine include a fuel consumption rate of 1.7 liters per hour.